December 7, 1941. The United States Pacific Fleet lies in ruins. Battleships capsized, thousands dead, and America's naval dominance shattered in a single morning. Japan's carrier strike force has rewritten the rules of naval warfare. But what Japan's admirals didn't know was that their greatest victory had awakened an industrial colossus that would crush them with a tidal wave of steel, rivets, and American ingenuity. Fade 2. Map of the Pacific, showing Japanese expansion. To understand how America won the Pacific War, we must first understand Japan's impossible position. By 1941, the Empire of Japan controlled vast territories across Asia and the Pacific, but faced a critical problem: resources. Japan's entire war strategy was built on a fundamental miscalculation. They believed they could strike America hard enough that the United States would negotiate a peace settlement. What they didn't understand was American industrial capacity and American resolve. Japan had begun the war with 6 large fleet carriers and 4 light carriers. Their crews were among the most experienced naval aviators in the world, but Japan's shipbuilding industry could produce only a handful of carriers during the entire war. Japanese fleet carriers at Pearl Harbor numbered 6, and they built only 7 large carriers during the war, with construction time of 2 to 3 years per carrier. Meanwhile, American shipyards were about to attempt something unprecedented in human history. Fade 2, 1930s footage of American shipyards, the Great Depression. The story of the Essex-Class actually begins years before Pearl Harbor, in the late 1930s. Naval planners saw war coming and began designing a new class of carrier that would define American naval power. The design incorporated every lesson learned from earlier carriers like the Lexington and Yorktown classes: longer flight deck, better armor, improved damage control, and crucially, it was designed for mass production. The keel of the first Essex-Class carrier, CV-9 USS Essex, was laid down at Newport News Shipbuilding on April 28, 1941, 7 months before Pearl Harbor. But it was the attack on Pearl Harbor that transformed the Essex program from an ambitious project into an industrial crusade. Within weeks of Pearl Harbor, President Roosevelt and Congress unleashed the full might of American industry. The Essex-Class program exploded from an order of 4 carriers to 13, then 17, then 24. What America did between 1942 and 1945 remains one of the greatest industrial achievements in human history. We're talking about shipyards that had built 1 carrier in 3 years, now being asked to build them in 18 months. And they did it. The numbers are staggering. While Japan struggled to replace its losses, America was preparing to launch a carrier fleet that would blot out the sun. Fade 2. Shipyard footage. Workers flooding into factories. The Essex-Class revolution happened in shipyards across America. Newport News in Virginia, Brooklyn Navy Yard in New York, Bethlehem Steel in Quincy, Massachusetts, and the Philadelphia Naval Shipyard. 24,000 tons of steel, 888 feet long, capable of carrying over 90 aircraft, and they were building them simultaneously. A former riveter recalls, "I was 19 years old when I started at the shipyard. We worked 10, 12-hour days, 6 days a week. You'd look down the ways and see 3, 4 carriers being built at the same time. We knew every rivet we drove, every plate we welded was bringing our boys closer to home." Women became nearly a third of the shipyard workforce. African Americans broke through segregation barriers to work alongside white workers in a common cause. The shipyards became microcosms of American society under pressure. Yes, there was still racism and sexism, but the urgency of war production forced a level of cooperation and recognition of talent that was unprecedented. Skills mattered more than skin color or gender, at least on the production floor. The construction process was standardized and accelerated. Prefabricated sections, assembly line techniques borrowed from automobile manufacturing, and round-the-clock shifts transformed American shipbuilding into a precision industry. Fade 2. Interior carrier footage. Technical diagrams. What made the Essex-Class truly revolutionary wasn't just that America could build them fast, it was that they were better than anything Japan had. An Essex-Class carrier was a mobile airport with teeth. The flight deck was wooden, but underneath was armored steel. Elevators were bigger and faster, the island was streamlined, and the damage control systems were generations ahead of Japanese designs. Compartmentalization was key. The Essex was divided into hundreds of watertight sections with sophisticated firefighting systems, redundant pumps, and emergency generators. Essex-Class specifications included displacement of 27,100 tons, length of 888 feet, speed of 33 knots, capacity for 90 to 100 aircraft, crew of 3,400, and range of 20,000 nautical miles. Japanese carriers, by contrast, had open hangar bays for faster aircraft operations but terrible damage control. One bomb in the wrong place could turn a Japanese carrier into an inferno. The Essex could take punishment and keep fighting. Fade 2. Launch ceremonies. Carriers sliding into water. USS Essex was commissioned on December 31, 1942, just over a year after Pearl Harbor. She was the first of a flood. Lexington in February 1943, Bunker Hill in May, Yorktown, Intrepid, Hornet, Franklin, Ticonderoga, Randolph, Hancock. The names honored fallen ships and American heroes. Each one represented thousands of workers, millions of man-hours, and America's industrial might made manifest. A former Essex navigator remembers, "The first time I walked aboard Essex, I couldn't believe the size of her. Everything was new, modern, efficient. We knew we had the best ship in the world. The question was whether we could match the Japanese in skill and courage." By the end of 1943, 5 Essex-class carriers were operational. By mid-1944, there were 10. By war's end, 17 had joined the fleet, with more under construction. Japan, meanwhile, had lost 4 of their 6 Pearl Harbor carriers at the Battle of Midway in June 1942. They would never recover. Fade 2. Combat footage. Pacific Island chains. The Essex-class carriers entered combat in 1943 during the Central Pacific Campaign. Operation Galvanic, the invasion of the Gilbert Islands, marked their combat debut. The Essex carriers revolutionized carrier warfare. They could launch larger strikes, sustain operations longer, and absorb damage that would have sunk earlier carriers. At Tarawa, they provided continuous air cover that was simply impossible before. But it was 1944 that proved America's industrial advantage. The Battle of the Philippine Sea in June, known as the Great Marianas Turkey Shoot, saw American carrier pilots, launched from Essex-class flight decks, shoot down over 600 Japanese aircraft while losing only 123 planes. A former Hellcat pilot recalls, "The Japanese pilots we faced in '44 weren't the veterans from Pearl Harbor. Those men were dead. These were kids with minimal training, flying inferior aircraft against our Hellcats, launched from the finest carriers ever built. It was a massacre." Japan had lost not just carriers, but the irreplaceable, experienced pilots, maintenance crews, and the industrial capacity to replace them. American carriers could rotate back to Pearl Harbor, take on fresh air groups, and return to combat. Japanese carriers, if damaged, might never sail again. Fade 2. Kamikaze footage explosions. In October 1944, Japan unveiled their desperate final weapon, the kamikaze. Suicide pilots who would deliberately crash their aircraft into American ships. The Essex-class would face its ultimate test. USS Franklin was hit by 2 bombs off Japan in March 1945. Over 800 men died. The ship became an inferno, listing heavily, dead in the water. By all rights, she should have sunk. Franklin's survival is a testament to Essex-class design. The compartmentalization, the damage control training, the redundancy built into every system, it all worked. Crews fought fires for hours, shored up bulkheads, and kept her afloat. She made it back to New York under her own power. Bunker Hill, Enterprise, Intrepid, Hancock. Multiple Essex-class carriers took kamikaze hits. Some were knocked out of action for weeks or months. But remarkably, only one Essex-class was lost to enemy action during the entire war. USS Princeton, sunk by a Japanese dive bomber in October 1944. Out of 24 ordered, 17 commissioned before war's end. Operations spanning the entire Pacific theater, only 1 lost. Meanwhile, Japan had lost all of their Pearl Harbor carriers and struggled to field any functional carrier force at all. Fade 2. War room maps, statistics overlays. The numbers tell the story of how America won the carrier war. Let's look at production from 1941 to 1945. Japan built 7 fleet carriers, 8 light carriers, and 5 escort carriers for a total of 20. The United States built 17 operational Essex-class carriers, 9 Independence-class light carriers, and 122 escort carriers for a total of 148. America built more than 7 times as many carriers as Japan, But it wasn't just quantity, it was quality, training, logistics, and replacement capacity. Japan's economy was roughly 10% the size of America's. Their steel production was a fraction of ours. They had fewer machine tools, less oil, limited rubber, and were fighting a war on multiple fronts. Once the war became an industrial contest, Japan had already lost. Each Essex-Class carrier represented 24,000 tons of steel, 40 miles of electrical wiring, 5 million man-hours of labor, and $78 million, equivalent to over $1 billion today. And America built 17 of them in 3 years, while simultaneously building battleships, cruisers, destroyers, submarines, and landing craft, not to mention the entire European theater arsenal. Fade 2, September 2, 1945, Tokyo Bay. On September 2, 1945, Fleet Admiral Chester Nimitz stood aboard the battleship USS Missouri in Tokyo Bay as Japan formally surrendered. Overhead flew hundreds of American carrier aircraft from the Essex-Class carriers that had brought them to this moment. The Essex-Class carriers had launched strikes against Japan itself, supported every major amphibious landing from Tarawa to Okinawa, and swept Japanese naval aviation from the Pacific skies. A veteran remembers, "When we anchored in Tokyo Bay, I looked around at all those carriers, Essex, Lexington, Bunker Hill, and the others, and realized we'd done something that would never be done again. We'd built a fleet from nothing and conquered an ocean." Fade 2, post-war footage, Korean War, Vietnam. But the Essex story didn't end in 1945. These ships would serve America for decades. They fought in Korea, Vietnam, and served as recovery vessels for the Apollo space program. The Essex-Class was so well designed that with modifications, they remained relevant for 40 years. Some served into the 1980s. That's unprecedented for a weapons system to remain effective across 4 decades of technological revolution. The last Essex-Class carrier, USS Lexington, was finally decommissioned in 1991, nearly 50 years after the class first entered service. She now serves as a museum ship in Corpus Christi, Texas, where visitors can walk her decks and see the ship that won the Pacific. Fade 2. Modern footage of museum carriers, slowly dissolving to archival footage. The Essex-Class revolution teaches us enduring lessons about industrial might, innovation, and determination. Japan made a strategic bet that America lacked the will to fight a long war. What they missed was that America had something even more powerful than will: capacity. The capacity to turn factories into shipyards, to train housewives as welders, to design, build, and deploy a fleet of supercarriers while fighting on 2 fronts across 2 oceans. The Essex-Class carriers didn't just win World War II, they defined what American naval power would mean for the rest of the century. Every supercarrier we build today is, in some way, a descendant of that revolutionary class. In the end, Japan's admirals were right about one thing. Pearl Harbor changed everything, but not in the way they imagined. It awakened a giant who would answer their 6 carriers, with 17 Essex-Class alone, and over 100 more besides. This is how America outbuilt Japan, not with one miracle weapon, but with the miracle of American industry, innovation, and indomitable will. The Essex-Class wasn't just a revolution in naval warfare, it was the industrial muscle of democracy made manifest in steel and rivets. And when the smoke cleared over Tokyo Bay, the world had learned an enduring lesson. Never bet against American workers, American engineers, and American determination. The scale of American industrial mobilization during World War II remains almost incomprehensible even today. When the first Essex-Class carrier, USS Essex herself, slid down the ways at Newport News Shipbuilding in July 1942, she represented just the beginning of what would become an unstoppable tide of naval power. The shipyards worked around the clock, 3 shifts a day, 7 days a week. Welders, who had never seen a ship before the war, were now constructing vessels that displaced over 27,000 tons. The sound of riveting guns and welding torches never stopped, creating a constant industrial symphony that could be heard for miles around the major shipyards. Each carrier required an astonishing array of components and systems. The propulsion system alone was a marvel of engineering. 4 sets of geared turbines generating 150,000 shaft horsepower, capable of pushing these massive ships to speeds exceeding 33 knots. The steam plants consumed thousands of gallons of fuel oil per hour, requiring massive fuel bunkers that could hold nearly 6,000 tons of oil. giving these ships the range to cross the Pacific multiple times without refueling. The electrical systems were equally impressive, generating enough power to supply a small city, with backup systems and redundancies built in at every level. The flight deck itself was a technological achievement that redefined naval aviation. Stretching over 870 feet in length and 147 feet at its maximum width, the wooden planked deck was suspended above the steel hull by an intricate framework of support beams and shock absorbers designed to handle the brutal impacts of carrier landings. The deck could accommodate up to 90 aircraft, though typical air groups numbered around 70 to 80 planes, depending on the mission profile. 3 elevators, each capable of lifting a fully loaded bomber from the hangar deck to the flight deck in under 20 seconds, kept aircraft flowing during combat operations. The armament package on an Essex-Class carrier reflected hard lessons learned from earlier battles. 12 5-inch dual-purpose guns in twin mounts provided the main anti-aircraft and surface defense, capable of firing 22 rounds per minute per gun to altitudes of 37,000 feet. These were supplemented by dozens of 40mm Bofors guns in quad mounts and 20mm Oerlikon cannons positioned around every exposed area of the ship. As the war progressed and the kamikaze threat intensified, carriers returned from combat and emerged from refits bristling with even more anti-aircraft weapons, some carrying over 150 individual gun barrels. The construction process required unprecedented coordination. Steel mills in Pittsburgh and Gary produced the specialized armor plate. Electrical manufacturers from across the industrial heartland supplied miles of cabling, junction boxes, and control systems. Optical companies produced the gun directors and fire control systems. Engine manufacturers in multiple states built the massive turbines and reduction gears. All of these components had to arrive at the shipyards in precise sequence, and the logistics operation to coordinate this supply chain was itself a major achievement of American industrial planning. Training the crews posed another massive challenge. An Essex-Class carrier required a complement of over 3,400 officers and enlisted men to operate effectively. These weren't just sailors, they were specialists in dozens of technical fields. Aviation mechanics who could tear down and rebuild aircraft engines in the rolling confines of a ship at sea. Radar operators who could track dozens of targets simultaneously on primitive cathode ray displays. Fire control directors who could calculate ballistic solutions for anti-aircraft guns while under attack. Damage control teams trained to fight flooding, fires, and structural damage while keeping the ship operational. The Navy created an elaborate training infrastructure to produce these specialists, from basic training facilities to advanced technical schools that rivaled any civilian institution. The pilots flying from these carriers represented yet another dimension of American advantage. While Japan struggled to replace its losses of experienced aviators, America built a pilot production system that generated thousands of highly trained naval aviators annually. Flight schools across the southern United States worked continuously, taking raw recruits and transforming them into carrier pilots through progressive training that emphasized standardized procedures and intensive practice. By 1944, American carrier pilots arriving at the fleet had hundreds of hours of flight time, while their Japanese counterparts were sometimes being rushed to combat with fewer than 50 hours. The logistical network supporting these carriers at sea revolutionized naval warfare. Previous naval operations had been constrained by the need to return to port for fuel, ammunition, and supplies. The Americans developed underway replenishment to a fine art, with dedicated oiler, ammunition, and supply ships capable of transferring everything from fuel oil to ice cream to fighting ships, while both vessels steamed alongside each other at 15 knots. This meant carrier task forces could remain at sea for months, maintaining constant pressure on Japanese positions without retreating to distant bases. The air groups embarked on these carriers evolved rapidly throughout the war. Early war Essex-Class air groups included F-6F Hellcat fighters, SB-2C Helldiver dive bombers, and TBF Avenger torpedo bombers. As the war progressed, the mix changed to emphasize fighters as American control of the skies became overwhelming. By 1945, some carriers embarked air groups that were two-thirds fighters, reflecting the shift from balanced strike capability to air superiority and ground attack missions. The Hellcat alone proved devastatingly effective, achieving kill ratios of 19-1 against Japanese aircraft. Damage control systems on the Essex-Class incorporated lessons from earlier carrier losses. Coral Sea and Yorktown at Midway had shown how vulnerable carriers were to fire. The Essex design included extensive compartmentalization, with hundreds of watertight compartments that could be sealed independently. Fire suppression systems included foam generators, sprinkler systems, and portable firefighting equipment staged throughout the ship. Gasoline systems for aircraft refueling used closed systems with inert gas blanketing to prevent vapor explosions. These measures proved their worth repeatedly as Essex-Class carriers absorbed terrible damage and survived. The protective systems extended beyond fire suppression. The underwater protection system featured multiple layers of empty and liquid-filled compartments designed to absorb torpedo explosions away from vital machinery spaces. The armor belt protected engineering spaces and magazines from shell fire and bomb hits. The armored flight deck, while not as heavily protected as British carriers, was strong enough to resist most bomb hits and could be repaired quickly using portable steel plates and emergency patching systems that carrier crews drilled on. Constantly communication systems represented cutting-edge technology for the era. Each carrier bristled with radio antennas and radar arrays, capable of coordinating air operations across hundreds of miles while simultaneously controlling defensive fighter patrols, directing anti-aircraft fire, and maintaining contact with other ships in the task force. The Combat Information Center, a darkened room filled with plotting tables and radar repeaters, became the tactical nerve center of the carrier, where commanders could track the battle situation and make decisions based on information that would have been impossible to gather. Just years earlier, the human cost of operating these ships deserves recognition. Despite all the technology and training, carrier operations remained brutally dangerous. Flight deck crews worked in one of the most hazardous environments imaginable, dodging propellers, avoiding jet blasts, handling bombs and rockets, and recovering damaged aircraft. Below decks, machinery spaces reached over 120 degrees Fahrenheit, with sailors working amid steam pipes, electrical systems, and heavy equipment that could kill with a moment's inattention. During combat, everyone faced the possibility of bombs, torpedoes, or kamikaze strikes that could turn a carrier into an inferno within seconds. The shipyard workers themselves formed a society unlike anything America had seen before. At the height of production, facilities like Newport News Shipbuilding, Bethlehem Steel's Fall River Shipyard, Brooklyn Navy Yard, and Philadelphia Naval Shipyard employed tens of thousands each. Newport News alone swelled to over 31,000 workers during peak wartime production. These weren't the experienced shipwrights of peacetime. They were farmers from Virginia, coal miners from West Virginia, shop clerks from Philadelphia, and women who had never held industrial jobs in their lives. They lived in hastily constructed housing projects surrounding the yards, entire new communities that sprang up to house the workforce. Shift changes looked like entire towns, moving as thousands of workers streamed through the gates. The welding revolution transformed ship construction. Before the war, ships were predominantly riveted, a slow process requiring teams of workers with specialized skills. Welding allowed faster construction and actually created stronger joints. The shipyards established welding schools that could take someone with no experience and certify them as a shipyard welder in 6 to 8 weeks. Women proved particularly adept at welding, their smaller hands and patient attention to detail making them exceptionally skilled at the intricate work required in tight spaces. By 1943, women made up nearly a third of the shipyard workforce. They welded in the double bottoms of ships, in narrow machinery spaces, and in the confined areas where fuel tanks met hull plating. The material science behind these carriers represented years of metallurgical advancement compressed into wartime urgency. The steel plates forming the hull weren't uniform. They were specified differently for every section of the ship. The outer hull plating needed ductility to resist cracking from wave action and combat damage. The armor belt required hardened steel that could resist shell penetration. The flight deck needed steel that could handle repeated impacts from aircraft, weighing several tons landing at closure rates of 30 feet per second. Each type of steel had different carbon content, different alloying elements like manganese, chromium, and nickel, and different heat treatment requirements. The steel mills had to produce these specialized plates in massive quantities while maintaining precise specifications. The propulsion machinery deserves particular attention for its engineering sophistication. The 4 propeller shafts, each over 20 inches in diameter, extended from the engine rooms through the hull via massive shaft alleys. These shafts had to be perfectly aligned and balanced. Any vibration at high speed could literally tear the machinery apart. The propellers themselves, each weighing several tons and measuring over 17 feet in diameter, were precisely machined to exacting specifications. The reduction gears that connected the high-speed turbines to the slower-turning propeller shafts were mechanical marvels, containing hundreds of precision-cut gear teeth that had to mesh perfectly under loads, measuring in the thousands of horsepower. The steam systems supporting these turbines operated at pressures exceeding 600 pounds per square inch and temperatures approaching 850 degrees Fahrenheit. The boilers generating this steam stood 3 stories tall, containing miles of tubing through which water circulated, while being heated by oil-fired burners. Each boiler could produce over 40,000 pounds of steam per hour. The piping systems distributing this steam throughout the ship had to handle extreme thermal expansion, with special joints and supports designed to accommodate pipes that would lengthen by several inches when brought up to operating temperature. The insulation wrapping these pipes contained asbestos, a decision that would have tragic health consequences for sailors decades later. The aviation fuel system incorporated safety features born from harsh experience. Early carriers had lost aircraft and crew to gasoline vapor explosions. The Essex design used a closed system where aviation gasoline was stored in tanks surrounded by seawater or inert spaces. When fuel was pumped to the hangar deck for refueling aircraft, the pipes were constantly purged with carbon dioxide to prevent vapor accumulation. The fueling stations included automatic shutoffs if sparks were detected. The hangar deck itself had extensive ventilation systems that created positive pressure, constantly pushing any fuel vapors out through side openings rather than allowing them to accumulate in the enclosed space. Despite these precautions, aviation gasoline remained terrifyingly dangerous, its vapors explosive in concentrations as low as 1% in air. The ordnance handling systems moved thousands of tons of bombs, rockets, and ammunition throughout the ship. Magazines located deep in the hull, below the waterline for maximum protection, stored ordnance in carefully controlled conditions. Bombs were stored with their fuses separate, only being assembled immediately before use. Temperature and humidity were monitored constantly, as some explosives became unstable with age or improper storage. Elevators lifted ordnance from the magazines to the hangar deck, where aviation ordnancemen would load weapons onto trolleys and move them to waiting aircraft. During combat operations, these ordnancemen worked with stunning speed, arming dozens of aircraft in the time it took pilots to receive their briefings. A single mistake, one dropped bomb or mishandled rocket, could destroy the ship. The radar systems bristled from every high point on the carrier. The SK air search radar, mounted on the mainmast, could detect aircraft formations at ranges exceeding 100 miles under good conditions. The dish rotated continuously, sweeping the sky while operators below studied the green phosphorescent displays for the telltale blips that indicated aircraft. The SM height-finding radar complemented the search radar, determining the altitude of detected contacts by using a beam that could be tilted vertically. Fire control radars for the gun systems used entirely different technology, with smaller dishes that could lock onto individual targets and track them through evasive maneuvers, feeding continuous position data to the gun directors. The Combat Information Center evolved from a minor auxiliary space on early carriers to the tactical heart of the ship. In this darkened room, illuminated only by plotting lights and radar displays, the carrier's operations officer and his team maintained the tactical picture. A large vertical plotting board showed the positions of all friendly ships, known enemy forces, and detected aircraft. Talkers with sound-powered phones maintained contact with every station on the ship, relaying information and orders without depending on electrical power that could fail in combat. The fighter director officer controlled the ship's defensive fighter patrols, vectoring them toward incoming raids using radio calls that became legendary. Bogies, bearing 350, Angels 15, distance 40 miles. Many bogies. The catapult systems represented relatively crude but effective technology. Unlike modern steam catapults, Essex-Class carriers initially relied on hydraulic catapults that could accelerate a fully loaded aircraft to flying speed in about 60 feet. The catapult track ran along the flight deck, with a shuttle that attached to the aircraft's landing gear. When fired, hydraulic pressure drove pistons that yanked the shuttle and aircraft forward, with acceleration forces exceeding 3 times gravity. Pilots braced themselves as the catapult fired, experiencing a brutal shove that could cause blackouts if they weren't prepared. The catapult crew, working in a small sponson alongside the flight deck, maintained these systems and operated them with split-second timing during launch operations. The arresting gear system caught landing, aircraft using thick steel cables stretched across the aft portion of the flight deck. These cables, each over an inch in diameter, were connected to massive hydraulic cylinders below deck. When an aircraft's tailhook snagged a cable, the hydraulic system absorbed the energy of an aircraft weighing several tons, moving at over 100 miles per hour, bringing it to a stop in about 300 feet. The forces involved were enormous. The cables could exert tensions exceeding 40,000 pounds. Cables broke regularly despite their strength, whipping across the deck with lethal force. The barrier system, consisting of multiple cable barriers that could be raised amidships, provided a last line of defense if an aircraft missed all the arresting wires or landed without its tailhook down. The flight deck crew evolved their own culture and practices born from the intense danger of their work. Color-coded jerseys identified each crew member's role: yellow for flight deck officers and plane directors, green for catapult and arresting gear crews, red for ordnance handlers, purple for aviation fuel crews, brown for plane captains, blue for tractor drivers and elevator operators, and white for safety and medical personnel. This color system allowed instant identification during the choreographed chaos of flight operations, when dozens of aircraft might be landing, refueling, rearming, and launching simultaneously. The noise made verbal communication impossible, so the crew developed an elaborate system of hand signals that could convey complex instructions across the flight deck. The air wing maintenance crews performed miracles of improvisation and skill. Aircraft engines required overhauls every few hundred hours of operation, meaning engines were constantly being removed, rebuilt, and reinstalled. This work happened in the confined spaces of the hangar deck, often while the ship rolled in heavy seas. Mechanics worked by flashlight during nighttime operations, their hands covered in oil and hydraulic fluid, rebuilding engines with tools that slid across the deck with each roll of the ship. They fabricated parts from scrap metal when supplies ran short, improvised repairs using materials never intended for aircraft, and somehow kept air groups flying through conditions that would have grounded civilian aviation. The ship's galley and food service operation fed over 3,400 men 3 meals per day, requiring industrial-scale food preparation. The galleys contained massive stoves, ovens, and steam kettles, capable of cooking thousands of portions simultaneously. The ship stored thousands of pounds of fresh, frozen, and dry provisions in refrigerated and dry storage spaces throughout the vessel. Menu planning required careful calculation to ensure nutritional adequacy while managing limited storage space. Fresh fruits and vegetables were consumed first after leaving port, followed by frozen provisions, with the crew subsisting on canned and dry goods during extended operations. The bakers worked overnight, producing hundreds of loaves of bread daily. Despite the challenges, the Navy prided itself on feeding sailors well, understanding that morale depended partly on decent food. The medical facilities aboard an Essex-Class carrier resembled a small hospital. The sick bay included an operating room with equipment for major surgery, a dental office, a pharmacy, recovery wards, and isolation spaces for infectious diseases. The medical department, led by a senior medical officer and staffed by multiple physicians, dentists, and hospital corpsmen, handled everything from routine sick call to combat casualties. During major battles, the sick bay could be overwhelmed with wounded sailors and downed pilots recovered from the sea. The medical staff trained constantly for mass casualty situations, practicing triage procedures and emergency surgery techniques. They hoped never to use. The construction of a single Essex-Class carrier involved coordination between hundreds of subcontractors scattered across the entire United States. The massive turbine generators came from General Electric facilities in Schenectady, New York, where engineers had designed units specifically for naval service that could withstand the shock of nearby explosions and continue operating. These generators weighed dozens of tons each and required special railroad cars for transport to the shipyards. The reduction gears, precision mechanical components that meshed thousands of gear teeth under crushing loads, came from specialized manufacturers who had perfected techniques for cutting and heat treating these massive gears to tolerances measured in thousandths of an inch. The electrical system aboard an Essex-Class carrier was staggeringly complex, consisting of multiple independent power distribution networks designed with redundancy at every level. The ship operated on 450-volt direct current for major machinery and 120-volt alternating current for lighting and auxiliary equipment. Switchboards located throughout the ship allowed damage control parties to reroute power around damaged sections, isolating electrical fires while maintaining power to vital systems. The wiring itself ran through over 40 miles of conduit, with junction boxes every few feet containing connections that had to be individually solid and insulated. Electricians spent months just running and connecting these cables, working in spaces so confined they could barely turn around, in temperatures that regularly exceeded 100 degrees even during construction. The ventilation system moved millions of cubic feet of air throughout the ship every hour. Massive blowers drew fresh air from intakes positioned high on the island's superstructure and forced it through ductwork that branched to every space aboard. In the tropics, where carriers often operated, interior temperatures without ventilation would quickly become lethal. The system included dust filters, moisture separators, and in some spaces, primitive air conditioning units that used seawater cooling coils to drop temperatures in the Combat Information Center and radio rooms, where electronic equipment generated intense heat. The machinery spaces received dedicated ventilation that created positive pressure, helping to suppress fires by limiting oxygen availability while simultaneously exhausting heat and fumes from the massive boilers and turbines. The damage control organization aboard an Essex-Class carrier represented a complete fire department and emergency repair service existing within the ship itself. Damage Control Central, located deep within the ship and heavily protected, maintained communication with damage control parties stationed throughout the vessel. Each party consisted of sailors specially trained in firefighting, shoring damaged bulkheads, plugging holes in the hull, and emergency repairs to vital systems. They had access to emergency equipment lockers containing portable pumps, wooden beams for shoring, welding equipment, sheet metal and tools for emergency patches, firefighting foam generators, breathing apparatus and medical supplies. During combat, these men stood ready at their stations, knowing they might be called upon to fight flooding in darkness, battle gasoline fires that could consume a ship in minutes, or shore up bulkheads while seawater poured through torpedo damage. USS Bunker Hill suffered similar devastation when two kamikazes struck her within minutes of each other in May 1945, killing nearly 400 men and wounding hundreds more. The impacts started massive fires that consumed the after portion of the flight deck, destroyed dozens of parked aircraft, and set off ammunition and aviation gasoline. The heat grew so intense that aluminum aircraft structures melted and steel deck plates glowed red. Yet the crew fought back, pumping seawater onto the fires for hours until the flames were controlled. The ship's structure, though heavily damaged, maintained its integrity. The engineering spaces continued running, providing power to pumps and ventilation fans that made the difference between survival and catastrophe. The construction techniques used in building these carriers evolved rapidly as experience accumulated. Early hulls in the class took over 18 months from keel laying to commissioning. By mid-war, the shipyards had refined their methods so dramatically that later Essex-Class carriers were completed in under 15 months, despite increased complexity in their electronics and weapon systems. The shipyards developed modular construction techniques where entire sections of the ship were fabricated separately and then lifted into place by massive cranes. Gun mounts were assembled and tested ashore, then installed as complete units. Equipment was pre-fitted into compartments before those compartments were welded into the hull structure. This approach dramatically reduced the time ships spent on the building ways. The process of fitting out a newly launched carrier transformed an empty steel hull into a functioning warship through the efforts of thousands of workers over many months. Immediately after launch, while the hull still sat pierside, workers swarmed aboard to install the internal systems. Pipe fitters ran thousands of feet of piping for fuel, water, steam, hydraulics, and compressed air. Each pipe had to be precisely bent, fitted, welded, and tested for leaks under pressure. The boilers and turbines were lowered through deck openings, positioned exactly on their foundations, then connected to the network of pipes, electrical cables, and control systems that would operate them. The steam lines connecting boilers to turbines had to allow for several inches of thermal expansion while maintaining perfect alignment, requiring special expansion joints and support systems that were themselves minor engineering. Achievements. The installation of the island. Superstructure represented one of the most visible and complex phases of construction. This multi-deck structure housed the bridge, chart room, signal bridge, primary flight control station, and numerous other operational spaces. It was fabricated separately from the hull and then lifted by crane and welded into place on the starboard side of the flight deck. The position and design of the island created aerodynamic effects that influenced landing approaches, and designers spent considerable effort optimizing its shape and placement. Inside the island, spaces were crammed with equipment: navigation instruments, engine order telegraphs, helm controls, signal lamps, radio equipment, radar displays, and the myriad controls needed to operate a vessel this complex. The aircraft elevators represented remarkable feats of engineering in their own right. Each elevator platform measured roughly 50 feet by 40 feet and had to lift loads exceeding 30,000 pounds from the hangar deck to the flight deck, a distance of over 20 feet in 20 seconds or less. The elevators used counterweights and powerful electric motors driving cable systems that had to be perfectly synchronized to prevent binding or tilting. The edge of each elevator platform had to align flush with both the hangar deck and flight deck when in position, requiring precision that seems impossible given the size and weight involved. During heavy seas, the ship's flexing hull would distort the elevator opening slightly, and the elevator mechanisms had to accommodate this movement without jamming. The communication systems extended far beyond simple radio and telephone. The ship's interior communication system used sound-powered phones that required no electrical power, relying instead on acoustic energy from the speaker's voice to generate a weak electrical current sufficient to drive a receiver at the other end. These systems remained functional even when the ship's electrical power was completely lost, allowing damage control coordination during catastrophic damage. The general announcing system could broadcast to every space on the ship simultaneously, allowing the officer of the deck to pass information to the entire crew. During general quarters, this system announced incoming air raids with the dreaded call that sent every man running to his battle station. The navigation systems combined traditional celestial navigation with emerging electronic aids. The ship's navigator maintained a detailed dead reckoning plot using the ship's speed, course, and time to track position. This was verified periodically by celestial sights using sextants to measure the angles of the sun, moon, planets, and stars above the horizon. In combat zones where maintaining radio silence was essential, celestial navigation became the primary means of determining position. The navigator also had access to radio direction finding equipment that could take bearings on known radio stations, and later in the war, Lauren long-range navigation systems that provided electronic position fixes accurate to within a few miles. The meteorological office aboard each carrier employed trained aerographers mates who prepared weather forecasts essential for flight operations. They released weather balloons to measure upper atmosphere conditions, plotted weather maps from radio reports received from shore stations and other ships, and briefed pilots on expected conditions. Weather forecasting in the Pacific presented unique challenges with massive storm systems that could appear with little warning. Typhoons posed existential threats to the fleet, with wind speeds exceeding 150 miles per hour and waves tall enough to sweep aircraft off flight decks. The Third Fleet nearly lost multiple carriers to a typhoon in December 1944, when the formation steamed directly into a massive storm, with destroyers capsizing and fleet carriers rolling through angles that brought their flight decks nearly vertical. The photographic laboratory aboard each carrier processed thousands of aerial reconnaissance photographs. Pilots returning from strikes carried cameras that had recorded bomb damage, enemy installations, and potential targets. These films had to be developed immediately, often while the ship was still at general quarters, so that intelligence officers could assess the results and plan follow-up strikes. The photo lab worked in complete darkness except for safe lights, developing film in chemical baths and producing prints on an industrial scale. During major operations, the photo lab might process hundreds of photographs daily, each one potentially containing information that could affect tactical decisions. The printing facilities aboard included equipment for producing charts, operation orders, intelligence summaries, and the ship's newspaper. Mimeograph machines and offset presses churned out thousands of pages daily. Before each operation, every pilot received detailed charts showing targets, navigation checkpoints, friendly forces positions, and planned routes. These had to be printed accurately, with no errors that could lead aircraft astray. The ship's newspaper, usually published daily when the ship was at sea, maintained morale by reporting war news, sports scores from home, and ship's news. These simple newsletters, often just a few mimeographed pages, provided an important psychological link to normalcy. The library and recreation spaces, though modest, served important functions for crew morale during long deployments. The ship's library carried several thousand books, magazines, and technical manuals that sailors could check out. Reading materials were supplemented by movies shown nightly on the hangar deck when flight operations permitted. The movie screen would be rigged, benches and chairs arranged, and hundreds of men would gather to watch Hollywood films that might be months old, but provided a few hours of escape. The Navy recognized that maintaining morale required attention to the psychological needs of thousands of young men confined aboard ship for months at a time.